In this lecture, we are going to look at how to build a recommender system using deep learning. This lecture is going to walk you through a prepared Colab notebook, although a very good exercise, which I always recommend, is once you know how this is done, to try and recreate it yourself with as few references as possible. As usual, you can look at the title of the notebook to determine what notebook we are currently looking at. So none of the imports are too surprising, so let's start with downloading the data. Now, this data is hosted at grouplens.org, and we'll be looking at the famous MovieLens 20 million dataset. Note that there are multiple versions of the MovieLens dataset, and most tutorials and courses use the version of the dataset which only has 100,000 ratings, but that's kind of lame, so we're going to demonstrate that we can do better. Now, since this is a zip file, we're going to unzip it. So you'll see that it comes with quite a few files. I'd recommend looking at these since I've already done the hard work for you by figuring out which is which. But you want to do that yourself at some point since you know that's part of being a data scientist. So next we do an ls to see what we now have in our working directory. Next I load in the data using pandas. And of course the data is a CSV. So the first column is the user ID. The second column is the movie ID, the third column is the rating, and the fourth column is the timestamp. So if you wanted to make some kind of really complex recommender system that maybe recommends the right thing at the right time, you could take into account the timestamp or the order of the events as they occur. But that's not really a thing that people usually teach in recommender systems, so we're not going to discuss it. Next, we recognize that although the dataset already uses integers for the user IDs and movie IDs, they might not be in the format that we want. Remember what these integers are eventually used for. They're used to index an embedding. So user ID 0 will index the first row, user ID 1 will index the second row, and so on. So think of a really non-ideal scenario. Let's say you have 100 users, but these 100 users have the IDs 1 million, 1,000,001, 1,000,002, and so forth. Well, what happens is that since each ID must be an index into an array, that array must have size 1,100,000. That's about 1 million rows of wasted space that you won't be using. Therefore, you would like your user IDs to be numbered from 0 up to n-1. The thing is, we can't just trust that the data is formatted in this way. In fact, I would recommend checking to verify this for yourself as an exercise. In any case, that's what this next block of code does. So I've commented out some code that you might use if you wanted to implement an index assignment from first principles using the apply function. Of course, if you read the documentation for long enough, eventually you'd stumble upon this useful thing where you can just cast the entire column to be a pd.categorical object, which automatically assigns integer IDs starting from 0. Then we can grab those IDs by calling .cat.codes. So next, it's the same story for the movie IDs. Again, as an exercise, you want to verify that the original IDs were or were not in the format we would like them. Next, since our data is currently in a data frame, we're going to split them into individual NumPy arrays. We can do that by calling .values on the relevant columns. Also, we're going to center the ratings data, which is part of the standardization process. The reason I'm not also dividing by the standard deviation is because in recommender systems literature, results are often reported in terms of the root mean squared error, the RMSE. Of course, this metric is reported on the scale of the original ratings. So if we change the scale, our results won't be directly comparable to other results. One alternative is to just scale your predictions and targets back before calculating the metric, but I leave that up to you. Next, we're going to find n, the number of users, and m, the number of movies. We'll also set d, the embedding dimension. The next step is to define our custom neural network for recommenders. In the constructor, we'll take in the number of users, the number of movies, the embedding dimension, and the number of hidden units. As an exercise, you could extend this to have multiple hidden layers. Inside the constructor, we create all the necessary modules. We have 2 embeddings and 2 linear layers. In the forward function, we define how to get a prediction given some input user and some input movie. As usual, it's important and useful to pay attention to the shapes. The u variable starts out as a numSamplesLength array, as does the m variable. The first step is to pass the user IDs and the movie IDs into their respective embeddings. This gives us 2 things of size numSamples by d. Next, we concatenate these along the 1 axis, and we get back a thing of size numSamples by 2d. After this, it's just a regular neural network. We pass it through a dense layer, do a ReLU, and then a final dense layer. Next, we create our device object. Next, we instantiate our model and move it to the GPU. Next, we create the loss and optimizer, and we shuffle the data. This is so that we effectively randomize the train test split. Next, we convert the data to torch tensors. Next, we create tensor dataset objects for both the train set and the test set. We define the train set to be the first 80% of the shuffled data, and the test set to be the last 20%. Next, we create data loader objects from our datasets. After this, things are more or less the same as usual. We create our training function, which by the way has to move the data to the GPU manually now. Previously, the special vision and text libraries were doing that for us. Next, we run the training function. You'll notice that I've got this special prun magic command. This is a profiler that tells us things like how much time we spent in each function. So why did I want to do this? Well, you'll notice that each epoch took quite a long time, over 5 minutes. I thought this was very strange. And so if you look at the outputs from the profiler, you can see that a majority of the time spent isn't coming from our for loops or the model, since our model is quite small. It's actually coming from the PyTorch dataset functions. So while you might assume that if you're using PyTorch, you should use PyTorch's data loaders, maybe that's not always the best idea. Sure, you could try to figure out if maybe there's some arguments we could have set to improve the performance or something like that, but for a basic dataset like this, you shouldn't have to. It should just work, which is the whole point of built-in functions in the first place. In any case, we'll discuss that more in the next lecture. So the final step is to plot the loss per iteration. And that shows us that the model has converged. Although you should pay attention to the final MSE here, because we are going to improve this value in the next lecture.